Hi. All right, we're going to do another 3-point cross question today. This one, I can't remember the date of the exam, but we're doing one of the practice exams I posted for you on Blackboard. And this exam has a question about owlbears. So I'm going to go to my answers layer here and let's plot out what we know. And remember, the whole purpose of this kind of exercise is to figure out whether you understand the concepts of recombination and linkage and how to identify recombinant and non-recombinant progeny and all of those good kinds of things. This is foundational to all of the cool stuff that people are doing in genetics right now in terms of genome-wide association studies and trait mapping and all of that kind of stuff. So let's have a look at what we know, and I thought it would be interesting / fun to for those of you that have social lives and significant others to sort of have a look at the fictional creature that we're talking about. So this is an owlbear, which apparently, according to my ridiculous question, is a magical beast that stalks the forests of this mythical world, which is actually the campaign setting for Pathfinder. Alright, anyway, we have a sorcerer that's interested in owlbear genetics, blah blah blah, mapping blah. Anyway, that's the idea. Once again, what you need to do first is map the alleles that are described up in this section of the problem to the phenotypes that are described down here. Okay, so let's just have a look at what I'm talking about. I just figured this makes it slightly less abstract. Maybe not. Anyway, with vision mutation. So, oh man, I can't write on this layer unless I rasterize it. Let's take a little moment here to there, all is well. I circled his eye, right? So we've got a vision mutation. The recessive allele confers vision in the dark by looking into the ultraviolet spectrum. Dominant allele, normal vision. The beaky mutant has a razor-sharp beak right here, whereas the dominant B allele confers a smaller, almost vestigial beak. And the aggro mutant, clearly this individual is aggro, I don't know, affects its behavior. So a recessive allele, the little a, has heightened aggression. All right, so that's an owlbear. I'm going to turn off that layer now, and I'll go ahead and get rid of the stuff that I drew on the owlbear. Okay. So what you need to do is map the alleles to this phenotype list. Right? Now, the first thing is, sometimes I throw this kind of a question is, C. Beloth crosses a male triple heterozygote, it's the genotype there, with a female triple homozygote, remember. What kind of cross is this? A lot of students want to write 3-point cross, which is technically correct, but really what I'm interested in you recognizing is that this is a test cross, because we are crossing it to a triply homozygous recessive individual. That means this individual, the mom, will give every one of her progeny, no matter what recombination happens, those 3 alleles. That's really, really important, because that means that the phenotypes here tell us exactly what the genotypes of these categories are as well. All right, so let's do this. And again, I suggest that you just start with one particular locus and map its phenotype on. So let's start with the vision locus. Wild type, no dark vision. Recessive, dark vision. Okay? So this is wild type, recessive, and so forth. Now, if you recall in another video, this process in a little bit, I made a mistake. So you want to slow down and do this correctly. All right, let's look at the beaky allele. So we've got a beaky mutant, which is little b, dominant, which is a small beak, is the big B. So here we go. Now it's possible you can't read these things, but you get the idea, I think. If not, you have to tell me in class so I can fix it. Right, and then the aggression mutant, we have docile, which is the big A, and aggressive, which is the little a. So big A, little a, and so forth. Okay, now that's not really worth any points, but it's important for later on in the problem. Right? You're just converting the text of the problem to the data in terms of mapping alleles onto phenotypes. All right, let's jump down to part B. Identify the non-recombinant progeny using the space to the right of the table. Again, I can't stress this enough. You must remember that the non-recombinant progeny will be the most common categories in a cross like this. So what you need to do is look for the largest numbers in number observed. And you can see the two largest categories in terms of frequencies here, this is number of baby owl bears, are these two. So this is sufficient for full credit. NR, non-recombinant progeny. Okay. Now, similarly, we have to identify the double recombinant progeny. Recall that recombination is more rare than no recombination, and double recombinant should be rare times rare, or even more rare. So the idea of identifying the double recombinant progeny is look for the least frequent individuals in terms of their phenotypes, and those are right here, 2 and 4. So if you just write DR and DR, that is sufficient for me to know what you're doing. All right, so we got 2, 4, 6 points bashed out already on this exam. We're feeling pretty good, but now the hard part starts. Write down the correct gene order. And once again, this is a part that I can tell you how to do it as many times as you like, but until you practice it, you will not figure it out. You need to sort of assimilate it in your mind in a way that makes sense to you. So the approach is, and I'm going to go ahead and switch to a different color here so you can kind of see me highlighting certain things, is to compare the non-recombinants to the double recombinants. All right? So let's take this non-recombinant. It's got a big D, big B, big A allele. So it's all wild type dominant alleles. And we'll compare it to its most similar partner in the double recombinants, and that would be this one. See how big D, that's the same, big B, that's the same. But look at this. There's the A locus, and it's different. Now, let's say you chose to look at this non-recombinant. Recessive, 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 right here. Look at this. Double recombinant, recessive, recessive, dominant. So, A is in the middle. Right? So let's write down the correct gene order, and again, the important thing is to get the gene that's in the middle correct so that you can calculate your distances. The actual order, DAB or BAD, doesn't really matter for this problem. Alright, so we've bashed out another 2 points. Excellent. This is usually the toughest part for students to grapple with, and like I say, if you don't practice it, it's going to be a shitty, oops, I shouldn't have sworn. Oh no, the video is ruined. It's going to be a bad day for you. So, all right, fill in the blank column of the table by writing the genotypes of each phenotypic class using the correct gene order. All right. Now again, I'm going to do something here that isn't necessary on the exam, but for teaching purposes, it's useful. every individual gets this chromosome from mom because it's a test cross. There's no genetic variation, right? So you do not have to write out this part if you don't want to on the test, if you're pressed for time or whatever, but for the purposes of this video we're going to do it. And notice what I'm doing. I am writing this in the correct gene order now. In extraordinarily bad handwriting. You're welcome. Is that a running joke yet? I don't know. Okay, so mom gave everybody the exact same chromosome. Because it's all recessive alleles, that means the phenotype here is a direct reflection of the alleles that they inherited from the male up here. So what you need to do is take these categories and rearrange them and write the correct genotype. So, and this is the part on the last video that I actually messed up. DAB, so dominant, 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 and recessive, recessive, recessive. There are our non-recombinants. Here are our double recombinants. Uh-oh, almost made a mistake. See that? Whew. Barely avoided embarrassment. Let me go ahead and just erase that. Okay, now D, little a, big B, and so forth. Almost done this part. And then finally that one. And I think that is all correct, but we will find out shortly when I attempt to look at the where the crossovers are. All right, so we've done that. That's worth 4 points. Now the hard part in terms of the calculations. We have to actually draw the genetic map by calculating the map distances. Right? Now this is the part where I'm not super efficient with using the space for handwriting, so I'm going to zoom in just a touch so that I can actually fit everything that's in here. So there's our gene order. We want to first calculate the distance between D and A. Okay. Now, in order to do this, I guess I skipped a little step here. So it's useful, but not required, to identify to yourself where the recombinations occurred to produce the gametes that these phenotypic classes have. So these are the non-recombinants, dominant, 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 or triply recessive. Right? Double recombinants are easy. I'm going to go ahead and get rid of this properties window. So these are the double recombinants. So we know they have 2 recombination events that produce these particular gametes. Here, though, you have to look a little bit more closely. So let's find the non-recombinants. We have dominant, 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 and here we have dominant, dominant, recessive. And so we've had a change here, and similarly we have triply recessive, and here we have recessive, recessive, dominant. So in these 2 categories, the B has switched places. And just logically, that must mean that the D has switched places down here. But let's just reassure ourselves that I didn't make a mistake. So we've got dominant A and dominant B and a lowercase d here. So look at the difference between this one and this one. So there and there. Now, when we go back, we can then say what categories were produced by recombination between D and A. So we've got this one and this one, 96 and 89, plus 89 plus, do not forget, we had recombinations here and here that are in the double recombinant, so you always have to count those, plus 2 plus 4. And then that's the number of recombinant progeny between those 2 genes. The total is 500, so the recombination fraction is let's see if we can do this in our head, because let's pretend I forgot my calculator and didn't bring it to the test. I forgot my calculator. Anyway, I'm not mocking you, except that I am. 96 plus 89 plus 2 plus 4. So 96 plus 4 is 100, 102, 182, 191 divided by 500. Now, you can probably do this in your head, but let's pretend that you were on the ball on Friday and you brought your trusty calculator. 191 divided by 500. 0.382. 3 significant digits is sufficient. If you multiply that by 100, that gives you 38.2 centimorgans. Okay? I am going to run out of room again because I cannot write small. Now, we need to calculate the distance between A and B. Same approach. Where do we see recombinations happening between A and B? Here. So 18, 21, and the doubles. So 18 plus 21 plus 2 plus 4. And we divide by the total number of progeny in the experiment. So 18 and 21 is 39, 41, 45. Divided by 500. I'm going to guess this is 0.090, but let's check. 45 divided by 500 equals 0.09. Math. Anyway, multiply that by 100 to convert it to map units, in this case centimorgans, and we have 9.0 centimorgans. And now we can draw our genetic map. So D to A is roughly that, and A to B is roughly, a third of it or a fourth of it, something like that. Okay. So this distance, 38.2 centimorgans. This distance, 9.0 centimorgans. And this distance is the sum. So that would be 47.2 centimorgans. And now you've drawn your genetic map, and everyone is happy. Last question. So sometimes I'll ask you coupling or repulsion, and sometimes I'll ask you interference. In this one, I've done coupling or repulsion. So recall, coupling means that all of the wild-type alleles are on the same chromosome and all of the recessive alleles are on the same chromosome. Repulsion means there's a mix of wild-type and recessive alleles on each chromosome. And to figure out which is which, you have to look at the non-recombinant progeny. All right, so we'll scroll back up here, and we've conveniently enough identified our non-recombinant progeny. And do you see these alleles? We've got these individuals are dominant, dominant, dominant. These individuals are mutant, mutant, mutant. They're all on the same chromosome. There's not a mixture. So this problem involves this male triple heterozygote is in coupling. All right, so the basic idea is to take, I'll just zoom out so you can see the whole page again. You have to map your alleles onto phenotypes, identify non-recombinant and double recombinant progeny, figure out what the correct gene order is, and write it down, write each category's genotype down here, identify where the crossovers happen, do your mapping calculations, and you're ready to roll. I guess I should put my name on the page section. I don't know, whatever. Alright, so as always, if you have any questions, just shoot me a text. And if there are other ways or other problems you want me to work in a video format, just let me know. Alright, now I'm going to fumble with all of the stuff to try to turn off this recording situation. I'm getting better at it though, I think. I don't know.